Assalamu alaikum. Hello everybody. Once again, a new video about sequences. So we have three exercises. The first one, let un and vn be two real positive sequences. So we will take here positive sequences such that un equal to a, which is less than v0 equal to b. A and b are positive since un and vn are positive. We define un plus 1 by the square root of un vn, and vn plus 1 is un plus vn divided by 2. Show that un vn converge and that they have the same limit. We will try to prove that that un or vn are increasing or decreasing. The second are decreasing. We try to find a relation between un and vn. Let us start by remembering that if we have the square root of a minus the square root of b, capital B, square, this is greater than or equal to 0, which is equivalent to a plus b minus 2 the square root of a b greater than or equal to 0. This is equivalent to a plus b divided by 2 greater than or equal to a b. From this famous identity, we can deduce that un plus 1 is less than or equal to vn plus 1 for all n greater than or equal to 1. And since u0 is less than v0, this means that it is for all n in n a natural number starting from 0. This is first. Second point, we have un plus 1, which is equal to the square root of un vn, and since un is less than vn, so this is less than un squared, which is equal to un. This means that un plus 1 is less than or equal to un for all n in n 0. The second remark, we have vn plus 1, which is equal to un plus vn divided by 2. Don't remember that vn plus 1 is less than vn plus 1. This is less than or equal to vn plus vn divided by 2, which is equal to vn. And this means that vn plus 1 here we have greater than or equal. This means that here we have greater than or equal. and here we have less than or equal for all n in and 0. The first cell, un is non-decreasing, and Vn is non-increasing. With the remark that un is less than or equal to Vn for all n in and up. Then un is non-decreasing and upper bounded is non-decreasing and upper bounded by, for example, u v1 by v0. So un is convergent. Vn is non-increasing and lower bounded by u0. So Vn is convergent. Both of them are convergent. How about the limit? We suppose that since it is convergent, so extra noise, we suppose that un converges to L1 and Vn converges to L2. This will give us L1 equal to the square root of L1 and L2 equal to L1 plus L2 divided by 2. Both equation gives us L1 equal to L2, and this gives us L1 equal to L2. This means that we have solution, and this solution prove that L1 equal to L2. This finished the first exercise. Let us move to the second one. Let us move to the second one. Let x be a real number such that x is strictly included between minus n and n is a natural number. Unx equal to 1 plus x over n power n, and Vn is 1 minus x over n power minus n. Show that Un and Vn are adjacent, so we have to speak about adjacent sequences. First of all, we consider Un divided by Vn. This is equal to 1 plus x over n power n divided by 1 divided by 1 minus x plus n, which is equal to 1 plus x divided by n power n times 1 minus x divided by n power n, which is equal to 1 minus x squared divided by n squared power n. Since x squared over n squared is less than 1, so this is greater than or equal to 1. So this means that un is greater than or equal to Vn. Vn is greater than or equal to Vn. Now, this is not less. 1 minus this is less. Sorry, once again, this is less than this is between 0 and 1, so this is less than. So un is less than or equal to Vn. Why? Because un divided by Vn is less than or equal to 1. This is first for all n in n. For all n in n. First remark. Second remark. We will prove that un is increasing or non-decreasing and Vn is non-increasing. Once again, we will use the magic formula which says that an is greater than or equal to gn. Geometric mean is less than or equal to arithmetic mean. Let us consider the n plus 1 root of 1, this is first, times 1 plus x divided by n power n. We have here n element, plus element, we have n plus 1 element. Using this formula, this will be less than or equal. How many elements do we have? We have n plus 1 element. N element plus n elements, n plus 1 element. The first element is 1. The nth remainder element are 1 plus x divided by n, so we have n times 1 plus x divided by n. This is equal to, abracadabra, we have 1 x divided by n plus 1. If we take power n plus 1, one will get 1 plus x divided by n power n less than or equal to 1 plus x divided by n plus 1 power n plus 1. This means that un is less than or equal to n plus 1 for all n in n. This means that un is non-decreasing. How about Vn? We will apply the same formula for 1 minus x power minus n. The same formula. We will apply it for 1 divided by 1 minus x power n. The same formula for this expression. It will be, this one will be non-increasing, non-decreasing. So the inverse will be non-increasing. We can say that Vn plus 1 is less than or equal to Vn for all n in n. To conclude, what do we have? We have un less than or equal to Vn. We have un is less than or equal to un plus 1. Vn plus 1 is less than or equal to Vn. Un is non-decreasing sequences and upper bounded, so it is convergent. Vn is a non-increasing sequences and lower bounded by u0 for u1, for example, so it is convergent. Both of them are convergent. Let us consider the difference between Vn and un. We have Vn minus un. This is equal to 1 divided by 1 minus x divided by n power n minus 1 plus x divided by n power n. This is equal to, this is equal to 1 minus x divided by n power n. 1 minus power, so 1 minus x divided by n square power n. Remember that this expression is between, it is between 0 and 1. And the maximum value of this one, maximum value, is attains at 1. So the maximum value for this is 1. And the difference between them is included between 1 and 0 and 1. So the maximum value is 1. So the difference, the maximum difference between them, it is equal to 0. The maximum difference. As an example to understand, if we take 0, 5 power n, this is less than 0, 5 power 2. If we take minus, this will be minus, and greater than, strictly greater than 2. It will be minus. If we take 1, it will be greater than 1 minus. So the difference here is the greater possible for n greater, the difference. What we can say? We can say that this difference, all this difference, is less than or equal. What is less than or equal? This is the little one. So the little one is 1 minus without power. So minus 1 minus x divided by n square divided by 1 minus x and power n. I recommend that you check this inequality once and twice to understand the trick. But since un is less than or equal to the n, so this is positive, and is less than or equal to x divided by n square divided by 1 minus x divided by n power n, and this goes to, since it is convergent, don't forget this. This is convergent, so it converges to a finite limit, but this one converges to 0, so we will have 0 divided by L, which is different of 0, and this is equal to 0. So here we verify the condition for adjacent sequences, which are actually just two. We need that one is increasing, the second is decreasing, and the difference between them is it goes to 0, but it is preferable, it is adequate if you verify that you check which is less than the second, to be sure that they converge to a limit, and we can use this idea here to conclude that it is equal to 0. So once again, think once and twice about this inequality. Let us move to the third and last exercise of this video. Let Q and A be two real numbers. We consider Sn equal to 1 plus Q plus Q power n. And we consider S index n P equal to Q power n plus 1 until Q power n plus P. First question, show that for all n in n, Sn is equal to this formula, 1 minus Q power n plus 1 over 1 minus Q, if Q is different of 1, and n plus 1 is n plus 1 if Q is equal to 1. We have Sn, which is equal to 1 plus Q plus Q power n. And we consider Qsn, which is equal to Q plus Q power 2 plus Q power n plus 1. We take the difference between them, then Sn minus Qsn, here we keep just 1, they will be constant except the last one. Then Sn is equal to what? Is equal to 1 minus Q power n plus 1 divided by 1 minus 1. In this case, for sure, Q is supposed to be different of 1. And if Q is equal to 1, we have to sum 1, 2. So here we have Q power 0, Q power 0, Q power 1 until n. So we have n plus 1 terms. In this case, we have n plus 1 times 1 if Q is equal to 1. This is the first formula. We deduce the limit of Sn, so the limit of Sn is equal to it is equal to 1 divided by 1 minus Q if Q is less than strictly 1. It is equal to plus infinity if Q is equal to 1. It is equal to 0 if Q is equal to minus 1, and n plus 1 is even. In this case, we have here 1 minus 1 power even, so 1 minus 1, and here we have 2. It is equal to minus infinity if Q is equal it is equal to 2 and 2, it is equal to 1. If q is equal to minus 1 and n plus 1 is odd. It is equal to plus infinity if q is greater than 1, or q is strictly less than 1 and n plus 1 is n. It is equal to minus infinity if q is less than minus 1 and n plus 1 is odd. I hope that I didn't forget any case. I hope that I didn't forget any case. You can check all the cases, as I am in a video, so it can be that I miss the case. I think that that is all the cases. Yeah. Q equal to minus 1 and plus 1 is even. Q equal to minus 1 and plus 1 is odd. Plus infinity if q is greater than 1 or q is less than 1, but n plus 1 is even. Q less than was minus 1 and n plus 1 is odd. How about if q is less than 1 and and it is equal to plus infinity? I think that this is all. Yeah, I think. I am not sure. The third question, even you can find if there is missing cases. How about the third question? When you watch a video like this, don't believe all what you saw. The author can be wrong in some details, so you have to have a critical mind. Don't believe all what you can saw. Watch and think at the same time. Watch and think. The third question deduce that for all q in minus 1, 1, s and p is less than or equal to 2, the absolute value of q power n plus 1 divided by 1 minus q. So here we have s and p. This is equal to q power n plus 1 plus q power n plus p, which is equal to, this is equal to q power n plus 1 times 1 plus q plus q power p minus 1. If we times by n plus 1, we find n plus p, n plus p. We know how to calculate this sum from the previous exercise. This is equal to n plus 1. times 1 minus q power p minus 1 plus 1 divided by 1 minus q. Q is less than 1 and greater than minus 1. So minus 1 is less than or equal, minus 1 is less than or equal to q power p less than or equal to 1. You can discuss all the cases, but this is the large interval on which q power p is. We can find sometimes that q power p is between 0 and 1. We can find that q power p is between minus 1 and 0. But the most, we are sure that q power p is between minus 1 and 1. If we take minus, it will be the same. It is symmetric. Then 1 minus q power p is between 0 and 2. If we divide by minus q, this will be minus q because this one is positive. Then S and P is less than or equal. This term is positive, just this one. If it is positive, it's okay. If it is negative, in this case, we can be sure that S and P is less than or equal to the absolute value of k power n times 2, 1 over 1 minus q. This is the solution of the proof or the solution of this question. The last, this is a little bit long video. The last question is an application. Define the nature of un, which is given by un. Un is defined by ln 2 divided by 2 plus ln 1 plus 1 over n 2 power n. We can remark easily that this is an increasing, non-decreasing sequences, because if we add un plus 1, it will be un plus ln 1 plus 1 divided by n plus 1 over 2n plus 1. So this is a positive term, since this is positive and this is greater than 1, strictly greater than 1. So it cannot be equal to 0. So this is an increasing sequence. If we prove that it is upper bounded, it will be convergent using the famous theorem. What we can show, un is positive, but it is less than ln, the natural logarithm, is less than 2 for all n, because this is less than 2. The maximum is 2. So this is less than or equal ln 2 times 1 over 2 plus 1 over 2 power n. So this is less than or equal to ln 2 times we have here times 1 divided by 2, 1 minus 1 divided by n power n we have n minus 1, so power n divided by, and 1n goes to plus infinity, this goes to 0, so it is upper bounded by ln 2 times 1 half. We have here 2 1, so 2, it is this is less than or equal ln 2. Since it is less than or equal to ln 2, so it is increasing and upper bounded, so it is convergent. Thank you very much. See you next time.